Welcome to
Okay.
Communicating Science and Reason. In this program, we aim to show the beauty of science and seek to encourage scientific thinking to the public. And for those who don't know him, Dr. Lawrence Krauss is an accomplished theoretical physicist and science communicator. He's an advocate for the public understanding of science, empirical data, scientific skepticism, and science education. He's previously taught at Arizona State University, Yale University, and Case Western Reserve University. So I want to begin by asking you, what are the most interesting advances in your field of particle physics?
Well, I think there are a number of frontiers in particle physics. One is trying to understand why the known forces, in particular the standard model of particle physics, which describes the three non-gravitational forces of nature, we have a wonderful theory called the standard model that really works too well, because there are lots of open issues. Why are there three forces? Why do they have different strengths? Why particles have mass that they have? Why they're the symmetries of the standard model. All of these things are left open, these questions, and we're hoping that when we push to a new energy frontier, we'll be able to answer some of those questions. So trying to understand the standard model and the nature of the particles and forces we know of is one frontier. The other is trying to figure out how to unify gravity with the other forces of nature, because we have quantum theories of all of the other forces, relativistic quantum theories that work very well, but we don't have a relativistic quantum theory of gravity. At least we don't have one that is clearly works in the space of three space dimensions in one time that we appear to live in. There are ideas for how to have a quantum theory of gravity, and they're very interesting, but they haven't yet demonstrated that they describe reality or solved any of those fundamental questions.
I believe that's called the grand unified theory, right?
Well, that's actually the grand unified theory is one that actually the first version of the grand unified theory is one that really unifies the three non-gravitational forces of nature. It turns out we have many reasons to think that those forces will be unified at a very small scale, about 16 orders of magnitude smaller than the size of a proton, and that's close to the area where we'll need a quantum theory of gravity. So we think that maybe gravity can be unified. But the first step is to just unify the other three forces, which we think can be unified, although we don't have any direct evidence yet and any really good theories. We have ideas. But bringing gravity in is a much more difficult task, because it goes beyond what's called quantum field theory, which is the formalism we use for understanding all the other forces in nature. So it's going to require a much more radical revolution to really bring gravity into the mix. And as I said, there are lots of ideas, string theory and other ideas that, and the reason to do that is not that we need a quantum theory of gravity to understand most of what goes on in the universe today. We don't. But if we want to understand the very beginning of the universe, we need a quantum theory of gravity. Just like if we want to understand the sort of the final stages of black hole formation, we need a quantum theory of gravity. On scales where gravity becomes sufficiently strong that you have to have a quantum theory. You have to have a theory that's consistent with quantum mechanics in order to understand how to describe it. So that's another area that's of great interest. And another area that's really been around for 50 years is the notion that we live in a universe full of matter, and that may not seem very strange to you, but matter and antimatter are virtually the same in fundamental physics. They have this antiparticles have the same mass as particles and largely the same interactions. But we live in a world of matter and not antimatter, not equal amounts of matter and antimatter, which is lucky for us, because if there was equal amounts of matter and antimatter, they would have both annihilated long ago and there'd be nothing left but radiation. But we still don't have a complete understanding of how you can start in an early universe with potentially equal amounts of matter and antimatter and end up with a universe that, as far as we can see, is primarily just matter. That's one of the big outstanding questions. Now, there's an area at the forefront that really then begins to merge physics and cosmology. There are two areas, and that's why I've worked for 40 years at the interface of physics and cosmology. And the reason is that to understand the universe on the largest scales, ultimately we have to understand the physics that governs the universe on the smallest scales, because the universe was once very much smaller and evolved. And there are two experimental or observational puzzles that are very big puzzles, and they relate to particle physics. One is that most of the mass in the universe around galaxies and clusters of galaxies is invisible. It doesn't shine. And we're reasonably convinced it's not made of the same stuff as you and I, not made of protons and neutrons.
Dark matter, right?
Dark matter, yes. We think it's a new type of elementary particle. And so we have theories for what it could be, and then there are experiments that are designed to detect it. And that's an important interface. And I've worked on both of those areas. And I expect in the next decade or so, we may be able to have an experiment that will detect dark matter. We'll see. I've been saying that for a while, so we'll see. But it's possible. But the other problem, which is much deeper and much more mysterious, is the fact that empty space has energy. The dominant energy in the universe resides in empty space, and that is strange in the extreme. And we first proposed it in 1995, and then the experimenters discovered that to be true in 1998. And it's the biggest mystery in science. We don't know why empty space has the energy it has. And I think that's a very deep question and a very deep puzzle that will take, I suspect it'll take a lot longer to solve that puzzle than it will the dark matter puzzle. That's called dark energy, by the way.
Yeah. And how do you believe astronomy and discoveries in outer space have impacted other fields of science? Like, for example, astronomy heavily influenced the creation of ecology. How do you believe it affected other fields of science?
Well, I think astronomy, I mean, look, anytime astronomy basically is to try and understand the dynamics and physical processes that happen in space, and at the largest ends of it, a subfield of astronomy called cosmology is to discuss the whole universe. But clearly, if you're trying to understand that, the physics that's relevant for that can be very relevant for us. As I say, the discoveries in cosmology that we've made have dramatically impacted on particle physics. The fact that we're searching for dark matter, we think they're new types of elementary particles. The fact that we really have to understand quantum mechanics and gravity, probably if we're going to understand dark energy, is one example. But also, as we realize that there are now, almost all stars have planets around them, and there are 100 billion stars in our galaxy, and therefore probably 100 billion solar systems. And it's quite likely that there are other planets like that maybe are habitable and that may have life on them. We have to think more broadly than we do about life on Earth, but the questions are the same. How did life evolve? What options are there? What processes led to its evolution and its diversity? And so thinking about life elsewhere in the universe ultimately comes back to thinking about life here on Earth.
My other question to you is, in your opinion, what's the impact of social media and the internet in general on the transmission and retainment of information? Some think that the internet provides an easy to access source of information, while some think that the internet is full of bias and misinformation and is therefore disadvantageous to science. What's your take on this?
Well, the social media has had as you say, is a two-edged sword. In one sense, it's amazing. I was just talking to a friend of mine. It's amazing to think what young people have access to today. You have access to the whole world of information about physics and in some ways can study and have it be exposed to almost everything. When I was a kid, you had to go to a library and find some books, and even those were rare and few and far between. So there's incredible opportunities for building a knowledge base. But as you say, there's incredible misinformation. And so that we have to have a whole set of new tools that teach us how to distinguish the nonsense for the sense, how to test the ideas that you read about and check multiple sources. So that aspect of the internet, that it's a source of misinformation and false facts, if you want to call it, or fake news, is a problem. But it's also an incredible resource, and we shouldn't forget that each of us every day uses it in ways that just seem, trivial now, even if it's just finding your way to the nearest store, or finding what time the nearest store is open. Those things 30 years ago, those tasks were much more difficult, if even possible. But there's another aspect of the social media, which is unfortunate too, in that social media has given everyone an opportunity, which is good in a way, everyone an opportunity to have a voice. But at the same time, it means that a few loud voices can have an impact that was impossible in the old days when there was just, say, television networks. And now you can have small groups of very noisy people who intimidate individuals and institutions. And we're seeing that, and that's really unfortunate, because we need to have a structure and institutional leaders that are in some sense are willing to stand up to mobs on social media, and that's a concern And I think it's going to iron itself out eventually, but right now it's a concern because it's affecting free speech, free inquiry, and individual rights.
Yeah, I want to ask you a question about your new book, The Physics of Climate Change. And so many public figures in science, technology, etc., such as Bill Gates or David Attenborough, have been currently interested and have been actively raising awareness and globally discussing climate change or global warming. What has inspired you personally to write your new book, The Physics of Climate Change?
Well, there were a number of factors. First, I've been thinking about this issue for a long time and been exposed to it in the sense of I was chair of the board of the Bulletin of the Atomic Scientists, the board of sponsors of the Bulletin of the Atomic Scientists for a dozen years. And we set the doomsday clock. And every year I'd have to face these existential challenges as we talked about what were the challenges facing humanity. And we'd bring experts in from around the world to help out and help explain. And so those were tutorials for me. And so I became very aware of what the issues were for climate scientists. And then what really, there were two things that caused me to write the book. First, a direct experience, having led a trip to Cambodia and Vietnam and the Mekong Delta this last year, which is really like a perfect storm of climate change. It's an area that's going to be impacted dramatically by sea level rise. And so that really brought it home, seeing the remarkable cultures and appreciating how much they'd overcome in the last century. And now they're facing a challenge which is due to something they didn't really create themselves. So that brought it home and made it personal and made it much more vital for me to be thinking about it, maybe considering writing it. And then the pandemic, I was at home. I had many other things canceled, and I tried to think, what could I do that might be useful? I'm not a first responder or a doctor, and I thought, well, maybe writing a book that does what I think is necessary, which is to talk about the science. Before you talk about policies, you have to understand what the underlying science is. And I thought it'd be an interesting challenge and fun to do. And I was able to do it really quickly because all of my other constraints were gone. I was able to write this book in 1/10 the time of what I would have normally done, where I had many other responsibilities and obligations and distractions. So I think feeling that it was a useful thing to do was important, and the right time to do it. Right now, politicians are deciding on policies, and it's really important that those policies are based on empirical reality. And I wanted to have a book to show people, anyone could understand the fundamental science behind climate change and enough to realize what the basic predictions are, and to see that it's not something in the future. It's not something that requires supercomputers. It's really based on 150-year-old physics, but some interesting physics, and people can understand. Anyone with a sort of a high school education can certainly understand the basic physics of climate change and see and compare the data. And there's lots of graphs and figures in my book so that people can see what the actual data is. So I thought it would be, then people of different political persuasions can decide what policies they want to enact, but we should all at least agree on the same set of facts.
On the subject of science and politics, do you think science is entangled with politics? And if so, do you think this is beneficial or disadvantageous to science?
Well, there's pluses and minuses. Look, all major political issues, if you want to think about it, are scientific in one way or another. Health, national security, the economy and technology in modern times, as well as climate change and energy. Energy is a basis of all economies. So in some sense, science and technology are always intertwined with what should be policy, public policy. But what shouldn't happen is that science shouldn't become embroiled in political issues. Science is neither left nor right, neither liberal nor conservative. It's there as a basis from which public policy can be derived based on empirical evidence and well-known understanding. And so the real problem is when science becomes embroiled in politics in a way that it shouldn't be. It should lay the basis of politics, but not become political itself. And unfortunately, in the current times, there are many areas where science has become political.
Another question I have for you is, in your adventures in science communication, what techniques do you use to combat mistrust in science and unscientific thinking?
Well, I've said this many times before. I'm an educator, and if the only tool you have is a hammer, everything looks like a nail. And I think the ultimate way is to educate people about the scientific process. Not the facts of science, but the way science works. the kind of thinking and the kind of questioning of yourself and checking your sources and retesting, and the fact that our thinking evolves. And I think that one of the easy ways that the scientific nonsense gets pervaded is that people don't appreciate what science is, that science is a process. It's not a thing, it's not a collection of facts which you can decide you agree with or disagree with. It's a process to understand how the universe works. And when you understand that process, you can sift the wheat from the chaff. You can separate the nonsense from the sense.
And so you worked with Dr. Richard Dawkins in helping people to think for themselves and to trust science. And what did you learn the most from that experience?
Well, we've worked together in a variety of cases, and it's been an enjoyable collaboration to reach out to the public. And I think what I really appreciated the most was that people were surrounded by groups that are either religious groups or otherwise are dominated by pseudoscience or superstition, often feel alone and helpless. And what I really appreciated was the fact that all the response to the movie we made and the lecture we've done, where people say, this made me realize that I'm not alone and that there are other people out there interested in this. And that gives people the kind of energy they need to keep going. So I hadn't realized the sense of isolation that people in a lot of places around the world have because they feel alone or feel like they're bad people for asking questions. They often are told that they're bad people for asking questions about a variety of subjects, and whether it's religious or nowadays more even social subjects. And so we need to. I became more energized and realized that the public efforts that I do are useful because they can help convince people that asking questions is not a bad thing.
And on the subject of science communication, how are you able to maintain a consistent balance between providing an audience with detailed information about a subject, but not so much to make them forget about the aforementioned information?
Well, it's always a juggling fact, and sometimes you do it right, and sometimes you don't. You learn as you go on. I think what is really important is to not provide people a comprehensive understanding. It's hard to do that in a book or a popular book or a lecture, but to give people a basic perspective of the key ideas, connecting them so they can see the flow of the ideas, and then motivating them so that if they want to actually learn the details, they can go on the web or in further books and learn. So I think I think of it as more as motivating, and also presenting some of the major contradictions and inconsistencies that many people have, the biases that people have that are wrong. So trying to correct those misconceptions. So that's the prime thing: correcting misconceptions and giving people a basic perspective. I think that, and then I try in my books, more so than my lectures, to provide, there's extra there so that the people who really have a good basis have some meat that they can chew on. So you try and hit many different levels. And in my books, there's some things that I hope everyone will understand. There's some things that not everyone will understand, but I try and make it so that if you don't really understand that, you can skip over and move to something else and you won't lose the thread. But it's a learning process, and you learn by feedback too. Having given lots of lectures, you can sense what people can understand and what they can't understand. So it's like learning. It's learning.
Particle colliders have obviously had a massive effect on particle physics. What do you believe will be the next big stride in this field of physics-related technology?
Oh, who knows? As I often say, if I knew what the next big thing was, I'd be doing it. So that's what makes it a discovery. But I think there's discussions of some new types of colliders, a very large linear collider that's being considered that take us beyond what's being done at CERN. And I think we need to do that to be able to answer some of these fundamental questions. But there are new types of technology, new types of accelerator technology that are being considered all the time. There are tabletop experiments that are sometimes much bigger than a table, but we call them tabletop experiments that can nevertheless are extremely sensitive. Atomic physics experiments are incredibly sensitive. And with some of these type of things, we can probe things which we might otherwise need an accelerator probe, because the accelerator gets us to high enough energy to probe very small distances. But what these sensitive experiments can do is look for processes that happen at very small distances, but manifested at our distance scale in very, very rare events. But if you have a very, very sensitive detector or experiment, you can look for very, very rare processes, or else you can measure certain quantities to 10, 12, 13, 14 decimal places, and the new physics may come in the 14th decimal place. We're seeing that right now. There's something called the anomalous magnetic moment of the muon, which appears to be inconsistent from earlier experiments with our fundamental theoretical predictions for what that should be. It's basically muon's like a little magnet, and the strength of its magnetism is slightly different than our theories would predict. Now, in the old experiments, it was slightly different, but not different enough that you could be concerned there was some problem. But if we can do a more careful experiment, and these new careful experiments are now being done, that may demonstrate an inconsistency between the prediction and the experiment, it'll point to new fundamental physics.
In your opinion, what's the most significant, impactful scientific theory or discovery in science in the past century?
Oh, I don't think I hate to say this, but I don't think in terms of most or high, I don't label things that way with a hierarchy. People always ask me that. There are lots of incredibly important discoveries, and they've each had, lots of different implications. I mean, the discovery that DNA was the double helix and the basis of genetics was incredibly important in the 1950s. But obviously, discoveries of quantum mechanics have revolutionized not just our theoretical picture of the world, but our technology. I couldn't be using any of the devices I'm using now to talk to you were it not for quantum mechanics. They all rely on quantum mechanical properties. There have been lots of discoveries that have changed our picture of the world. Like 100 years ago, the consensus wisdom in science was the universe was static and eternal and had only one galaxy in it. In 1922, that was the picture of the universe. And now we know that the universe is expanding. It has a age of 13.8 billion years. There's 100 billion galaxies. Our picture of the universe has changed dramatically. So there have been so many important developments that it's incredibly exciting, but I hesitate to say one is more important than the other.
And so I want to end this interview on a happier note. How do you think is the most likely way the universe will end?
How will the universe end? Most likely
Yes.
it'll end badly. That happy note. It's likely that it'll end badly. The universe will end with a whimper, not a bang. Namely, the most likely possibility, and I say most likely because we can't prove it's the case. And that's important because it means there's some internal mysteries, which are nice. But most likely, based on what we measure now, the universe will go on expanding forever. The galaxies move farther and farther apart, faster and faster apart, till most of them disappear from our view. And in our own galaxy, which will collide with some other galaxies to form one big galaxy, eventually the stars will burn out and the universe will become cold, dark, and largely empty. And that's the future. But happily, that future is trillions of years in the future. So it shouldn't stop you from enjoying your brief moment in the sun right now.
But if the universe is continually expanding, wouldn't there be new stars and galaxies to form?
Not necessarily. The space between the galaxies will be expanding, and the galaxies become rarer and rarer and rarer. And so in any kind of conceivable time frame, actually the universe really will become empty. The distance between galaxies will expand and expand and expand. And in any given region that you can see, you're likely to see only one galaxy, the galaxy that you live in. And that's lonely. Now, stars will keep forming, and will keep forming for at least 2 to 10 trillion years. There'll be stars forming in our Milky Way galaxy. So that on that time scale, there'll be stars forming, and there'll be planets around those stars, and civilizations can form. So that's a long time. But eventually star formation will stop at our galaxy, and matter will collapse in the center to make the black hole in the center of our galaxy larger and larger. And eventually that black hole will evaporate, we think, and then that'll be it.
Dr. Krause, thank you so much for being with us today. Have a good day.
Well, it was a pleasure to talk to you.